Welcome to springlib.
Hello everyone, today we're doing chapter 18, problem 8, and this problem asks us to draw the stepwise mechanism for the following reactions. What we have here is a benzene ring, some sort of alkyl halide, loose acid, to form some sort of alkyl substituted benzene group here. So what we know is that we're going to have Friedel-Crafts alkylation occurring for this mechanism. And what we have here, if we draw this out in skeletal form, you have this alkyl halide group, but then when we draw our product in skeletal form, we see that we have something that kind of differs in shape. So we know that this is going to be some sort of electrophilic aromatic substitution reaction going on. So this alkyl halide group must be our electrophile, and the benzene is going to be our nucleophile. So in essence, we need to form some sort of carbocation here. So if our leaving group leaves in this situation, we would get a primary carbocation. So we know that also if our nucleophile attacks this, we wouldn't get this terbutyl group that's shown here. So what we know is that there must be some sort of hydride shift that occurs to now move this carbocation to the tertiary carbon here, in which when our nucleophile attacks, we would get this compound here. So let's draw the mechanism of forming first our electrophile. So we have our alkyl halide plus our Lewis acid. And we know that now chlorine with its lone pair electrons can attack our Lewis acid. And now because aluminum now gained 2 electrons from chlorine, it's going to be have a minus charge, but now chlorine lost those 2 electrons, so it's going to have a positive charge. And now we can say that the 2 electrons in the sigma bond between the alkyl group and the halide are going to leave to form a primary carbocation. But we know that primary carbocations don't form, so something must push this chlorine to pop off and to leave. So what's going to push it is the 1,2 hydride shift and rearrangement of a carbocation. So we're going to have shifting of this hydrogen to this carbon when you're making a bond. When you make a bond, you break a bond. So now the sigma bond can fall off and go on to this chlorine atom here. And now what we formed is that tertiary carbocation that we were talking about earlier, plus now a conjugate base. So now we formed our carbocation electrophile. So now we can do part 2. Part 2 is the actual nucleophilic attack on our electrophile, the nucleophile in this case being the benzene ring, and specifically the pi bonds on the benzene ring. And this is our electrophile. So now using one of those pi bonds, we'll go through a carbon atom, making a new bond here. But in that process, we lose aromaticity, and we actually gain a carbocation in our 1 benzene ring, and we can actually stabilize this carbocation by resonance. So you can stabilize this by resonance by moving around these pi bonds to form 2 more resonance stabilized structures. But regardless of which form resonance, if you draw the resonance or not, we need to remove this carbocation to regain aromaticity on our compound to form this final product here. And what we know is that we say that this is a Lewis acid catalyst. So what we know is that we reform catalysts in all reactions. So we must reform this aluminum trichloride. And the one way that we can do that is, well, we can draw our conjugate base like this. And now what we can say is that using those 2 electrons as making this aluminum negative, we can actually pick up this proton here, making a bond. You make a bond, you'll break a bond. So then you reform your pi bond on your benzene ring to reform the aromaticity and form the product of interest. this pi bond's reformed. You get your alkyl substituted benzene, but now you form HCl and you reform your acid catalyst.